All right, let's work through this problem that's in our notes. This is actually a one sample Z test using a proportion, slightly different than our one sample T test, right? Because in this case, we're actually interested in some hypothesis test around a proportion. All right, so here's our example. A marketing research consultant hired by Pepsi Cola Company is interested in knowing if the proportion of customers who favor Pepsi Cola over Coke is different than 50%. Right, so we're talking about a proportion of customers, proportion of consumers. That's what we're interested in knowing, right? We're trying to prove that it's different than 50%. If it was 50%, then I would say, it's exactly equal. And Pepsi Cola says, well, we think it's different. It could be that we have a smaller market share or a bigger market share than Coke, and we're not sure which, so it's different. We're trying to find that it's different. That's what we're trying to prove. So randomly sample 250 consumers from the market under investigation, polled them, and it turns out 0.464 preferred Pepsi in a taste test, 46.4%. So use a 10% level of significance, test the appropriate hypotheses to help answer his question. All right, so the notes have it all, but I'm going to actually do this in Excel. We'll do it one more time. The notes are all there except for the Excel stuff. So let's jump over to Excel. So I actually made some data up for us to sort of get some practice with as if this were real data. So this is the kind of results we'd get, right? We get some results that say, either Pepsi or Coke. Way down here we start getting Coke. And we had, from the problem, 250 people. All right. So step one, before we actually have to go collect this data, we could create step one, find a null and alternative hypothesis. A null hypothesis would say, well, remember the question, so back to the question, is we're trying to find that the difference, the proportion of consumers who favor Pepsi over Coke is different than 50%. So whatever it is we're trying to find belongs in here. This is P instead of, we're not going to mu anymore, we're talking about P. P is not equal to 0.50. That's what different from means, right? It doesn't say that it's less than 50% or greater than 50%. It says it's different than 50%. So the null hypothesis then is that P is equal to 50%, right? So that's what we're after. This is really little p. P is not equal to, and then because it's not equal to, this is a two-tailed test, right? All right, so there's step one. Step two then is we go collect the data. So we got the data, and then calculate our statistics. So we have to first find P hat, right? And then it would be good to get the standard error. P hat, we have to have an N in order to do that. So let's arrange these in proper order. And then in the notes, we talk about how we could go find a Z. There's not a whole lot of reason to do that for these types of problems. But, before we found a T, but the only reason we found a T was so that we could put it into the T dist function later on. Well, in this case, we're going to put these numbers into a norm dist function, and we don't need a Z to do that, right? So there's not a whole lot of reason to do that. But we could, but let's not do it. All right, so let's find the P hat. The problem actually gives us the P hat. Remember, the problem says that 0.464 preferred Pepsi in a taste test. But let's figure out how you would do it if you had real data. First, we would just find the count of all of our observations, right? Which would we have to use this actually for counting words. We have to use what's called count A. Forgot about that. Count A. 250. If we're counting words, we have to use count A. Counting numbers, it doesn't make a difference. So 250. And then we want to do a count if function, right? First we have to decide what's success, right? We're saying Pepsi is success. So we're going to say count all of these things, and then the criteria is Pepsi. Well, I can just point at one of these Pepsis over here, and it says 116. So that's great. That's not P hat, right? That's just the count of successes. So then we have to divide that by our N. Right, so of the 250, 116 told us Pepsi, so that's 0.464, that's exactly what the problem tells us, 0.464 preferred Pepsi. So that's how I would come up with my P hat if I had raw data, 0.464. Okay, great. The standard error then, remember how we did the standard error? It was like the square root of P hat times 1 minus P hat. That's our numerator, divided by N. All of that had to be square rooted. So there's my standard error. That's a pretty small standard error, 0.03. Considering our null is 0.50, now I can go 3% on either side there. So I can see right now that this is a little over 1 standard errors away. So it might be significant, it might not be. So it's kind of hard to tell right now. All right, so let's go to step 3. The problem actually says use a 0.1% level of significance. So step 3 was find alpha, right, or set alpha. So alpha, then we're going to use 0.10, which is the highest alpha you'll ever see. So most of the time you'll only see 0.05 and 0.01. Sometimes you see an alpha of 0.10. So in this case, we're okay to have a little bit more type 1 error. I mean, it's not going to like kill anybody if we have a type 1 error, for this problem. It's not even really, that important that it's super good science, because this is just a sort of a market share analysis type of thing. So a higher alpha is probably okay. All right, so step 4 then is to find a p-value. Find a p-value. I actually want to, before I do find the p-value for this specific problem, let's pretend instead that p-value is not equal to 5. Let's change the alternative hypothesis so that it's not a two-tailed test, and just do a one-tailed test first. We'll come back and do the two-tailed test, but I want to change it up to find the p-value for a one-tailed test. So instead of that, let's just say p is less than 0.50. Let's use that as our alternative hypothesis. So this would just be a one-tail, and it would be a left. One tail, comma, left test. Okay, so that's a little easier. In fact, that's what we already know how to do. Remember, we're going to use the norm dist function, right? So at the end of the day, what this looks like is, let's see if I can, let me draw a picture. Yep. Right, is that we're going to sort of draw a normal distribution. Yeah, that's pretty good. That has a mean, according to what our null hypothesis says, right? So a mean of 0.50. Mean of 0.50. And then we want to see what's the probability of something being over here for this problem for a left tail test, right? So something way out here. Find the probability of something to the left of that. The left of some sample. Well, we went and collected a sample. And what did our sample get? Sample got 0.464. All right. So all we want to do then is find the probability of something smaller than 0.464 if there's a normal distribution with 0.50 and a standard error of 0.03. So this is just a norm dist function that we've all got really good at. So there's nothing really weird here, right? So that's all we do. So equals norm dist. What we got, remember x, we can sort of think of what we got. We got p hat. What we expected to get? Well, we expected to get 0.50, right? That was our null hypothesis, 0.50, with a standard error equal to the standard deviation, and 1. 0.12. So this would not be significant, right, with an alpha 0.10. So that's a left tail test. Now, if I wanted a two-tailed test, then let's go back to my picture. Then what I'm interested in knowing is whether it's on the left tail or the right tail. Either one doesn't matter. But it turns out that I end up multiplying this by 2. Right. So the notes talk have some kind of funky formula in there that says, go find the left tail and the right side, the left side and the right side of your sample. And whatever one of those is smaller. So you can just look at it and say, well, the left side is definitely smaller. The right side is just 1 minus this, right? Whatever one is smaller, then multiply it by 2. So again, now let's go back to this two-tailed test. So this is, I should write this. This is for a one-tailed test. Two-tailed test, then, is really, it's just that number times 2. That's all it is. That's all a two-tailed test is. So what that means is that if a two-tailed test is basically twice as hard to prove than a one-tailed test. Twice as hard to prove, right? So I had to have twice as much evidence to prove that something has changed as opposed that something is just smaller or bigger than something. So a good way of thinking of two-tailed test when it comes to actually doing it is to just find the one-tailed test, right? That's the appropriate side, either left side or right side, and then multiply it by 2. Right, so just find, in this case, we can see, 0.46 is smaller than 0.50. So whatever size our sample comes out at, find the side, if it comes to the left of it, find the left side. If our sample came back and said, let's pretend like our sample was 0.55, right, then I would want to find the right tail and then multiply that by 2. Right, so that's how I get the two-tail test, is I multiply one tail by 2. All right, so that's it. So at the end of the day, we have a pretty high p-value. So step 5, we say there is not enough evidence to conclude that that the null is wrong. So we can't say the proportion of Pepsi preference is different from 50%. So we can't say that any different than 50% of the consumers prefer Pepsi in this given sample. Let's double check to see if that's what I actually wrote down. Yep, p-value 0.2549. Is that what we got? 0.25471. Oh, I wonder what we did. Do something different. Just want to make sure I got this right, because it's not quite the same as the notes. It's pretty close. Not quite the same. P hat times 1 minus p hat over n. So that looks right. All right, what could be that my notes just had some rounding or something, and so at the end of the day, that's probably what it was. I probably just rounded something. So that looks like it's still right. So because 0.25 is greater than 0.10, we cannot reject the null. So we conclude by assuming that the proportion of people who prefer Coke over Pepsi is equal to 50%. Or really, a better way of saying it is that we can't say that it's not. We can't say the alternative is right. And so in this case, we basically say that, no, that is right. So this is interesting. So, how do we actually prove this? Because look, 0.464 is different than 0.50, right? It is different. The way to really prove that it's different is to get a really big sample size, right? So 250 is pretty big. But, what happens if I get, let's just type this in, 0.464, because it's going to change. What happens if I have 2,500 instead of 250, 2,500? What that does is makes my standard error way small, right? And then look at this. Now everything is super duper significant. Why is that? Well, because that just shrinks everything way down, because my standard error gets really, really small. So if I were to actually sample 2,500 people, and I got a p-hat of 0.464, I would say, yeah, that's definitely different than 0.50. But because I only sampled 250 people, I can't really say that. So that's the idea, that as my sample size gets bigger, I can actually shrink, again, the same idea, as I can shrink the confidence level down, and I can end up getting sort of more significant results if my sample statistic stays the same. Right, so if this really is, if p really is 0.464, remember we're trying to estimate p. We don't know what it is. We think that it's not equal to 0.50. Well, as we sample more and more and more and more, get a bigger sample size, and it turns out that it really is not 0.50, then we have more and more evidence in that direction. All right, so hopefully that helps for this problem, and that's it.